Okay, so we're going to look at chemical kinetics today, and this is going to be a short slideshow. Well, I hope it's going to be short. It's going to be a short one that I'm putting together. I'm not going to cover all the first chapter. There's a whole lot of terms and kind of ideas, at least the first section of chapter 17 that you guys are going to be assigned to read. There's just a couple things that I wanted to talk about. One of them was on there's a few things that get a little confusing, and one of them is on reaction rates and what is a reaction rate and what reaction rate are we talking about? What is it the reaction rate of? So I want to talk about that. So hopefully clarify things for you and hopefully won't confuse you. But I did want to go ahead and take a little time and talk about that. But before we do that, I also wanted to talk about why we even care about um, studying chemical kinetics, also known as reaction rates, as your chapter is titled. Chapter 17 is on reaction rates. So let's talk about that first. Why would we even care about what reaction, how fast a chemical reaction go, what rate a chemical reaction goes? So the topic is chemical kinetics. And what is chemical kinetics? Well, chemical kinetics is, as you can see right here, the study of the rate at which chemical reactions take place. So I'm going to go ahead and get my pointer here. So we want to know basically how fast the chemical reaction is going to take place. Is it slow? Is it fast? Something that takes seconds, some milliseconds even. If it's something that takes, decades, years, decades. So that's what we're studying here. Now, the term rate, just to go ahead and clarify, the term rate describes the speed of change over an interval of time. And so anytime you're talking about how something's changing over time, you're talking about a rate. Okay, so, if you're talking about how fast you're moving, you're basically examining how your position is changing. From one end of the football field to the other end of the football field, you've changed 100 yards, and how long it took. Because, most people can walk, could move from 100 yards from one end of the football field to the other. But how fast that takes place is related to how long it takes. Right? The less time it takes means the faster you are doing it. So we're going to be looking at rates with respect to chemical reactions. And once again, why would you even care? Why do we care about how fast a chemical reaction takes place? Well, I forgot to mention that there's an equation. We'll be looking at this equation in a little bit more detail, just a little bit. I'll come back to that later. You may have heard the saying, diamonds are forever. Back before, at the beginning when I started teaching, there was like some commercials that would say diamonds are forever. They're selling diamonds. And, as is custom in our society, when somebody wants to get married, they will go ahead and buy themselves a diamond. Generally, the young men will go ahead and buy themselves a diamond, and they will give it to whoever they'd like to get married to. And, that's propose, and now you got the diamond ring, and now your fiancés, etc., and so on. So part of this symbolism of diamonds in an engagement is because they are forever, and they're supposed to symbolize a relationship that will be forever. But let me tell you, that's not always true. That actually isn't true. Diamonds don't stay around forever. They actually turn into what's known as graphite, which is basically what you find in your pencils. I think I've mentioned this a couple times in the class. Graphite is pencil lead. So diamond and graphite are two forms of carbon. In other words, they're allotropes of carbon, the two solid forms of an element. And diamond is the less stable form of carbon. Graphite is the more stable form of carbon. Okay, and so there's beautiful rocks. The difference between these two here, the beautiful rock on the left and the dark rock on the right, is not the atoms. They're both made of carbon atoms, but it's the way that the atoms are put together. And so Graphite's atoms are in a more stable configuration. Diamonds are not. In order to get diamonds, you basically have to take carbon and shove it underneath the ground under great pressure in order to turn into the diamonds. They are very rare for that reason, and therefore, because they're rare, they are also very expensive. But it turns out that if you were to go ahead and look up the free energies of formation of diamond and graphite, and you were able to calculate a delta G for this reaction, you would find that the delta G is negative 2.9 kilojoules per mole. What does that mean? It means it's spontaneous. Remember delta G, we just learned if it's negative, then that means that your reaction is spontaneous. It's going to happen on its own. So if this is going to happen on its own, if this beautiful rock is going to turn into this less than beautiful rock, at least, I guess beauty is in the colder, but everyone's got their opinion, I guess. Why would you even spend those thousands of dollars to get this diamond ring if eventually it's going to turn basically into pencil? Well, the answer to that is, and for those of you guys who have already bought a diamond ring or plan to buy one, don't worry. Your diamond will turn to graphite. However, the question you have to ask is, how long does it take? And the answer is billions of years. So this is not going to happen for billions of years. Throughout your lifetime and your wife's lifetime, that diamond ring is going to stay as a diamond. Throughout your children's lifetime, throughout your grandchildren's lifetime, and many, many generations afterward, it'll still be a diamond until it starts getting a little cloudier and darker. And eventually, after billions of years, it'll turn into this. It'll take a while. So as you can see, we have a chemical reaction that takes place, or at least a chemical process that takes place. The diamond is going to turn to graphite. And if this happened, in let's say even a week or a couple of years, then why would you pay to have this turn to that? But because the reaction is so slow, so what if it's happening? It's not gonna take place during my lifetime. So yeah, I'll go ahead and buy the diamond. Okay. As far as I know, as far as I care, it is forever. It's forever in my lifetime. That's one example of why we examine reaction rates. Here's the second one. So the substance here on the left of this arrow, the one reactant that we have here, is this is the chemical formula for trinitrotoluene. Actually, I think this is supposed to be C7, but no big deal. So this is TNT. Trinitrotoluene is known as TNT. And most people know it as TNT. You say trinitrotoluene, people go, what? So the acronym is TNT, and everybody knows, oh, it's an explosive. And it's an explosive because it's liquid, then we'll go ahead and get jostled, and it'll decompose, and it'll turn into all these gases, and it'll give off heat. And so here is a typical explosion from what a typical trinitrotoluene explosion looks like, or TNT explosion looks like. The delta H for this reaction is negative 14 kilojoules per gram. That means that every gram of TNT that's being given off, that detonates, is giving off 14,000 joules, 14 kilojoules of heat and energy. And you can see the big old fireball right there. All these gases are pushing all this heat out. And we know that can be pretty destructive. Okay, so, we can go ahead and calculate that. Now, there's a second chemical equation that we can look at, and that's this one. 4Fe plus 3O2 goes to form 2Fe2O3. Now, if you look at this one, you compare it to the first one. The first one has a delta H of negative 14 kilojoules per gram. The second one has a delta H of negative 29.4 kilojoules. So every gram of iron, basically here, is going to give off 29.4 kilojoules. That's twice the number of this TNT explosion. Wow, this reaction down here must be really violent, right? Well, actually, not so much. That is the chemical reaction for rusting that is occurring. Fe2O3 is the orange rust that you see in this picture. And the iron, when it goes ahead and reacts with oxygen, the oxygen oxidizes the iron to what we call iron 3 oxide or rust. Now, this is true. The delta H for the process of rusting is twice that of TNT. So eventually, 1 gram of TNT is only going to give off half the heat that 1 gram of iron gives off. The big difference is that the TNT, all this occurs in less than a second. All this energy, all this heat comes up right at you, right away, at one moment. This occurs here in weeks, months, even years. So this energy is kind of like coming out, but it's coming out slowly. It's kind of like, taking this one is more like taking a bucket, filling it, to halfway up, and then just dumping the whole contents of the bucket on someone. Get splashed with all of that water. This one is more like filling the bucket all the way to the top, not just halfway up, all the way to the top, but just dripping it, a little drip, 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 dripping it on someone's head. Yeah, you get wet, but it's dropped to really small for a long time. You won't even notice it. Same thing with the heat. So it's important to know how fast reactions take place because the consequences really depend on the rate, how fast this occurs. If this occurs in less than a second, well, you're getting all this heat at one time. But if it's occurring over months and years, then that's a lot of heat, but it'll dissipate by the time the next little bit of heat comes out. So all those things are important when you're when you're a pharmacist or a pharmacologist or even a doctor. I need to know how fast these medicines will work inside the body. So they have a thing called half-life, which is related to how fast the body breaks down the chemicals, and they need to know these things so that you can go ahead and they can know how much to prescribe you, how often. Otherwise, they can overdose if you don't take into account how fast these medicines work and for how long they'll work. All right, so those were a few examples of why we care about chemical kinetics. And I just thought it was kind of important to talk about examples to why. The other thing I want to talk to you guys about was the whole thing on reaction rate. What is a rate? Because it can get a little confusing. Okay. Now we're going to use the rate. I'm looking at this equation in the middle first here. The rate will normally just use the letter R, lowercase r, to represent rate. And what a rate is usually a change in quantity. And as you can see right here that I have this delta, remember, is the Greek letter that we use that represents change. So a change in quantity divided by a change in time. There are two types of rates that you can look at. You can look at an average reaction rate and instantaneous reaction rate. So an average reaction rate is a reaction rate that takes place over a long period of time. And by long period, it can be anything over more than a second. Because a lot of these reactions take place relatively quickly, that a second is like the reaction's over. So if you go ahead and try to measure a reaction over more than a second, you'll be calculating average reaction rate. An instantaneous reaction rate is what is the chemical reaction rate now. So I like to make a analogy with speed, with your car speed or velocity. Let's say that you're going to Disneyland or some other place, and you want to figure out what your average rate was. Well, the average rate's how far did you go? Let's say it was 30 miles. And how long did it take you? Half an hour. So if you go ahead and take the 30 miles that you moved, that you traveled, and you divide it by the half an hour, That's going to give you 60 miles per hour. Now, when you went, you probably didn't go 60 miles per hour for the whole way. You weren't your speedometer wasn't on exactly 60 miles per hour. There's times when you're going faster, times when you're going slower. Somebody had to stop off at the red light. So this is a number. The average reaction rate is a number that you can calculate that tells you, well, if I was going to get from my beginning point to my end point over this time frame, and if the reaction went the same speed the whole way, that's how fast it would have to go. Then there's the instantaneous rate. The instantaneous rate I compare to just looking at your speedometer. Right? So whatever the speed is right then and there, that is your instantaneous rate. And you're going to be doing some sample problems with the average reaction rate, because the average reaction rate you can calculate by using the equation where you get the quantity at the beginning, the quantity at the end, and how long it took. You can plug those in. That'll give you an average reaction rate. The math is pretty much like calculating a slope in a graph, the slope of a line in an average class, in an algebra class. Instantaneous rate requires equipment to measure it out. That one's kind of harder to measure out. If you know some calculus, you can probably do it just by doing calculations, but we're not there yet with calculus. The point is, rates are always some change in quantity over change in time. And you may see rates with all kinds of different units, so don't get confused. Here I put some examples. Change in quantity. What do I mean by quantity? Well, quantities could be moles, they could be grams, they could be moles per liter, so their molarity, modality, things like that. Any way that you can measure an amount of a substance, you can use that as the numerator of your rate. The denominator must be some type of time. And as we mentioned, some reactions are really fast, some reactions are really slow. So you might use seconds, minutes, hours, years, whatever is appropriate. Really depends on how fast the reaction is going. So moles per second, right? Quantity over time, grams per hour, quantity over time. Here, this is mass, this is moles, but still, they're quantities. Amounts of our substance that you can see it reacted or didn't. And molarity, or moles per liter per year, quantity over time. Okay, so those are what you can look for whenever you're asked for a rate or you're given a rate. You can tell you have a rate if you've got units that gives you a quantity divided by time. Now, the last slide I'm going to go over. What I'm trying to do here is to have you guys kind of start thinking about what does it mean when they ask you about the reaction rate? Because you should be asking yourself, okay, I've got a reaction rate. If you're given a reaction rate, I've got a reaction rate. But the question is, I've got a reaction rate of what? Rate of what? I mean, I have a reaction rate, but is this the rate of the whole reaction, or is it the rate of a specific substance in the reaction? Am I looking here? If I have this equation, 4Fe plus 3O2 goes to form 2Fe2O3. If I'm given the reaction rate of this reaction, am I looking at the reaction rate of iron? Am I looking at the reaction rate of oxygen, of iron oxide, or of something else? And let me explain first what I mean, and then we'll start trying to kind of put these things together. If you look at this equation, this is a balanced chemical equation, and it's got coefficients. So being a balanced chemical equation, 4Fe plus 3O2 goes to form 2Fe2O3. We know that those coefficients they can represent atoms and molecules, or they can represent moles. We'll use moles. So what this reaction is telling me is that when 4 moles of iron react along with 3 moles of O2, so I've got 4 moles of iron and 3 moles of O2, I put them together, I end up with 2 moles of Fe2O3. All this is happening at the same time. The 4 moles of iron turn into 2 moles of Fe2O3 when they're combined with 3 moles of O2. So as you can see, the quantities of iron are going to be different than the quantities of oxygen. It's going to be different than the quantities of Fe2O3. So when I'm given a rate, if all these reactants are reacting at the same time and there's different amounts of each, which one am I using in my reaction rate? Okay. And it turns out that you can calculate the rate of any specific substance in a chemical reaction. How much iron did I just use up over, a certain time frame, right? So let's say, you had this reaction taking place and 4 moles of iron reacted, right? We start off with 10 moles, you end up with 6 moles, and that took, let's say it took 6 months. And so that's 4 moles over 6 months. That's what 4, 6, 2/3 moles per month that of iron we're losing. In those same 6 months, we had 3 moles of oxygen react. So the rate of oxygen that reacted is 3 moles divided by 6 months, or what, 3/6, half a mole a month. So every month, 2/3 moles of iron reacted, and half a mole of oxygen reacted. You don't necessarily need to know how to do the calculations. I'm just kind of going over them right now, but just to let you know that the reaction rate for iron is different than the reaction rate for oxygen. And it's going to be different for the reaction rate of Fe2O3. In those 6 months where the 4 moles of iron were used up, they turned into 2 moles of Fe2O3. So 2 divided by 6 months, 2 moles of Fe2O3 divided by 6 months is 1/3 of a mole of Fe2O3 is formed. So each one of these substances has their own reaction rate. Now, there's also this fourth one here called the overall reaction. So if you're given a rate, are you given the rate of iron, oxygen, Fe2O3, or are you given the overall rate? Now, some people, because a lot of times you will get a number that says, oh, the rate of reaction is. You're like, okay, well, the rate of the reaction, is that the rate of iron, of oxygen, or Fe2O3? Many times it's the overall reaction rate, and unless they're specific about telling you that it's the rate of iron or oxygen or Fe2O3, you can assume that's the overall reaction rate. Now, what is the overall reaction rate, and how is it different from the others? It's related. And here in the parentheses, we tell you what the overall reaction rate is. It is equal to the rate of any substance in the equation whose coefficient is 1. Now, one thing you'll notice is that this equation does not have any substances whose coefficient is 1. It's actually probably an exception. Most equations have at least one thing in them that have a coefficient of 1. Not all of them. Maybe not even 80% of them, but a lot of them will at least have one substance plus, H2O or something or whatever with a coefficient of 1. So whatever the rate of the substance with the coefficient of 1, which we do not find in this equation, but if we had a second product whose coefficient was 1, whatever that rate of that substance is, that would be the rate of your overall reaction. But even without having a substance with a coefficient of 1, we can still calculate the rate of the overall reaction. So what I'm going to do is I'm going to use the letter R just by itself with no subscripts to represent the rate of the overall reaction. And all these rates of the substances within them are related to each other through the rate of the overall reaction. Because iron has a 4 in front of it, that means there's 4 moles of iron for every 1 mole of whatever would have had a coefficient of 1 over here, which means that in the same time frame, we're actually reacting 4 times as many moles of iron than 1. It was 1 mole of this imaginary substance over here. 1 mole reacted in those 6 months, and 4 moles of iron reacted. That means that there's 4 times as many moles of iron reacting. Its reaction rate is 4 times faster. The rate of iron is going to be -4 times the rate of the overall reaction. The R with no subscript is the rate of the overall reaction I have here. Notice also that I put a negative in front of the 4. And the reason I did that is because iron is a reactant. And you'll recall I just said, well, we start off with 10 moles, went down to 6 moles because reactants disappear, right? That's what reactants are. They turn into something else. They react and they turn into something else. So we tend to lose them. So whenever you're writing the rate of a reactant, you put a negative in front of it. Okay. If I were to go ahead and say it went from 10 moles to 6 moles, then what I'm actually going to get is minus 4 moles. 6 minus 10 is negative 4. So the rate of the iron is negative 4 times the rate of the overall reaction. Oxygen, O2, has a coefficient of 3. So its rate is 3 times as fast as the rate of some imaginary substance with a coefficient of 1. And so the rate of O2 is equal to negative 3 times the rate of the overall reaction. Once again, the rate of the overall reaction is the same as whatever substance has coefficient of 1. And in this case, we're using this imaginary second product that would have a coefficient of 1. The rate of Fe2O3 is twice that. The coefficient of Fe2O3 is 2. And notice that this is positive because Fe2O3 is a product, so it is being formed. Okay, so here we can relate the rates of each of the substances to the rate of the overall reaction. So you should always ask yourself, what was I given? Was I given the rate of the overall reaction, or was I given the rate of the specific substance in my chemical equation? And if we wanted to know what the rate of the overall reaction was, in this case, as I told you, we don't need to have a substance with a coefficient of 1 to know what the overall reaction is. All we have to do is solve for R. So if I know the rate of iron, I can solve for R. And in order to solve for R here, you're just going to divide by negative 4. When you do, the rate of the overall reaction is negative 1/4 the rate of iron. So I just take my rate of iron and I divide by 4, right? Or multiply by 1/4, which is the same thing, and multiply by negative 1, right? Remember that the rate of iron will be negative, so negative times the negative is going to give you positive. The rate of the overall reaction will always be a positive. Or if I had the rate of the O2, I would multiply that by 1/3 and negative 1/3, and that would give me the rate of the overall reaction. Or if I didn't have those two, but I had the rate of the Fe2O3, I would just multiply it by a half, and that would give me the rate of the overall reaction. All of these three R's that should be the same number. These are all different. But when you plug them into this equation, if it's the same reaction occurring, the same things happening, all the data from the same reaction occurring along the same time frames, then this should give you all three of these R's should be the same number. And we can even relate all these three things to each other because we can go ahead and make them equal to each other. Since they're all equal to R, and R is all the same, then we can equal them to each other. So I hope that was helpful. I hope it was not confusing, but actually clarified some things. I know your book starts off with some equations a little bit easier because they're 1-to-1-to-1 coefficients. Everything has a coefficient of 1. So the rates for all the substances are 1 at a time. But eventually you get to some problems where the rates are different because the coefficients are different. So therefore the rates for each substance is different. And you have to really think, okay, so what number, the number I was given, that's the rate of which one of these substances. Reactant, is it a product, or is it the overall reaction? Okay. All right. Well, thanks for listening. And once again, hope that was helpful.